Okay, guys, one last topic to discuss. This last topic is not a difficult concept, or excuse me, it's not a long concept to explain, but it can be rather difficult to understand. We did an activity in class that talked about the differences between intramolecular bonds and intermolecular forces. Okay, and of course, we remember an intramolecular bond is the bond that's between two atoms within a molecule. Okay, also intermolecular forces are forces which hold actual molecules. They stick other molecules to other molecules. Okay. There's four different kinds of intermolecular forces that we need to discuss. Okay. First, we have ion to ion. This is an extremely strong interaction because we have a positively charged ion attached to a negatively charged ion. Okay, very strong because you've got two fully charged things which are stuck together. Okay, very, very strong. This is going to happen in ionic compounds. Hydrogen bonding is the next strongest, and this is where you have a polar covalent molecule that has a hydrogen attached to either a fluorine, an oxygen, or a nitrogen. Okay, the way I like to remember this is H fon. H fon. Okay, if you have a hydrogen attached to any of those three atoms, then it can be a hydrogen bond. Okay, so what's happening here is you've got a hydrogen and then you've got an oxygen. Okay, oxygen is like a million times more electronegative than hydrogen is. So what's going to happen is all of our electrons are going to hang out around oxygen, and nobody wants to hang out around hydrogen. Okay, so this is going to cause this to be extremely partial negative and extremely partial positive. Okay, more so than in a regular polar covalent compound. Okay, so now what's going to happen is you've got this situation right here. Okay, and now this partially positive side is going to stick to the partially negative side of another one of those molecules. Okay, next we have dipole-dipole. This is the same exact idea as hydrogen bonding, but the difference here is that there's not a hydrogen attached to either fluorine, oxygen, or nitrogen. Okay, this is going to encompass all of your other polar covalent compounds. Okay, so let's say pH3. Okay, so if we've got pH3, looks like this. Okay, unshared pair. So I know that this is a polar covalent substance because I've got hydrogen, 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 unshared pair. I do have hydrogens, but they're not attached to either fluorine, oxygen, or nitrogen. So this is going to have it's still going to have what's called a dipole moment. Okay, my partially negative side is going to be up here next to phosphorus, and then I'm going to have three partially positive ends as well. So now these two molecules right here, these could interact with each other. Okay, you've got a partially negative end that can interact with a partially positive end. Okay. Lastly, we have London dispersion. London dispersion happens in all non-polar covalent molecules. Let me show you what's going on here. All right, so what's going on in a London dispersion force? This is where you have a non-polar covalent compound, something like, let's just do CF4, okay? Or let's do CH4, methane, okay? So here goes methane right here. I notice I do have four polar bonds, but the molecule as a whole is non-polar, okay? Now, here's what I've got happening. Right now, I've got electrons, which all of my electrons are evenly matched around this molecule. But what's going to happen is something called an instantaneous dipole moment. And what an instantaneous dipole moment is it's literally for an instant, you're going to have electrons which are going to be found mainly on one side of the molecule. Okay, it's kind of like if you're in my classroom and I have 200 2-year-olds running around the room. Okay, for the most part, if they're all running around the room, they're going to be pretty evenly dispersed, just like in a nonpolar molecule. However, if I were to take a snapshot, there is a chance that more of those 2-year-olds could be on one side of the room than on the other during that snapshot. Okay, that's going to cause in a molecule what's called an instantaneous dipole moment, where for at a moment this side could be partially negative and this side could be partially positive, and then the very next moment this side changes to partially negative and now this side's partially positive. Okay, so when you have multiple molecules that are experiencing these London dispersion forces, there's going to be a quick interaction here, and then a quick interaction here, and then a quick interaction here, and a quick interaction here. And as fast as that interaction occurs, it's going to go away just as quickly. Okay, and so now where these two were connected, now these two are connected. Okay, and then it's going to connect to one over here, and then it's going to attract to one over here, and then it's going to attract back to this one. It's going to attract back to that one, so on and so forth. Okay, so that's the idea behind the London dispersion forces. All nonpolar covalent molecules experience London dispersion forces, and they're very, very weak. Okay, it doesn't take a lot of energy to break those up. Okay, therefore they're going to have really low melting points and boiling points because of the fact that there's not a lot. It doesn't take much energy to break those forces. Ion to ion, you've got full positive, full negative. It takes a lot of energy to break those bad boys up. Okay, London dispersion, you've got like just this mild little attraction going on, so it doesn't take much energy whatsoever to break those apart. So let's take a look at these. Okay, it wants us to determine what our dominant intermolecular force is. In order to do that, I need to draw Lewis dot structures. Okay, so I've got sulfur. Where'd you go? There it is. H2S. Okay, and here's my Lewis dot structure. So now I know that this is polar. Okay, I know that it's polar covalent because I've got hydrogen, unshared pair, and hydrogen. So it's not all the same, so I know it's polar. So this is either going to be dipole-dipole or hydrogen bonding. Now, the first thing you're going to want to do is you're going to want to say, oh, it's hydrogen bonding because there's hydrogen. Well, remember H-FON, okay, it has to be hydrogen attached to either a fluorine oxygen or a nitrogen, so this is just dipole-dipole. CH4 is when we draw the Lewis dot structure. Okay, I see that it's hydrogen all the way around. Since it's hydrogen all the way around, then that means it's nonpolar. All nonpolar molecules experience London dispersion intermolecular forces. Okay, lithium bromide. Lithium bromide is an ionic compound. Okay, I already know that an ionic compound is going to experience ion to ion interactions. NH3, this is ammonia. Okay, when I draw my Lewis dot structure, I do see that it is indeed polar covalent. I've got hydrogen, so now I want to know, is it attached to either fluorine, oxygen, or nitrogen? It is, so that makes this hydrogen bonding. And lastly, I have CBr4. CBr, and Br. Okay, this is bromine, so it's nonpolar, meaning it's going to experience London dispersion forces. So now, let's ask ourselves, what's the strongest intermolecular force up here? Well, ion to ion is always the strongest, so I'm going to give that number 1. Okay, what's the next strongest? Hydrogen bonding is the next strongest, so that one's number 2. What's the next strongest? Dipole-dipole, so that's going to be number 3. What's the next strongest? London dispersion. Oh my goodness, how do I know which one is stronger? Let's go back to our little drawing here for a second, okay? If I have, let me get rid of that for a moment. If I have CH4, okay, let's say I've got CH4. Hydrogens are really, really tiny, right? Okay, so this is going to be a really, really tiny molecule. So here's my really tiny little CH4. And then I've got bromine, okay? And bromine is a much larger atom than hydrogen. Okay? And so what we're concerned about is the size of the instantaneous dipole moment, okay? This is going to have a very weak partial negative and a very weak partial positive on its instantaneous dipole moment, okay? This one, there's more space for the electrons to run about, so this one's going to have a greater partial negative and a greater partial positive when it forms its instantaneous dipole moment. So that is going to mean that this one would have a slightly stronger interaction than this one, okay? So what you want to do in that case is you want to look at the size of the peripheral atoms and determine, you would say that the one that has the larger peripheral atoms is going to be the one that's going to have the larger, the strengthier London dispersion force. Okay, so therefore I know that this one is going to be fourth. I lost my pen. Okay, this one's going to be fourth, and then the CH4 is going to be the weakest. Okay, so now what you can do is, here's this chart. You can pause where you need and get this chart filled in. And this is just a review over the things that we've talked about, and get that written in so that you have it for your notes. And that's it. So go Unit 6.